We propose AutoRecon, a fully automated pipeline for 3D object discovery and reconstruction. AutoRecon achieves background-free object reconstruction without manual annotation. Current object reconstruction methods are still not fully automated. Users need to manually annotate the region of interest to be reconstructed and perform background removal after reconstruction. Moreover, existing object segmentation techniques still produce noisy object masks. In this work, we propose a course-defined framework for the fully automated 3D object reconstruction. The foreground object is firstly localized and decomposed from the structure from motion point cloud. Then we reconstruct a background-free object model with decomposed neural scene representations. Here are coarse decomposition and background-free reconstruction results of AutoRecon on the BlendedMVS dataset, and more results on the CO3D dataset. Let's review a typical object reconstruction pipeline. Given multi-view images, we recover poses and the coarse structure in point clouds with structure from motion or SLAM algorithms. Then, we annotate the foreground object region on point clouds or delicate user interface for foreground annotation. Following, we reconstruct the annotated region of interest with neural scene representations with differentiable renderers. The reconstruction results normally still contain backgrounds, and one need to remove the background with mesh manipulation. In an ideal object reconstruction workflow, the following characteristics are desirable. Firstly, we want to reconstruct layered or decomposed representations to facilitate scene composition and editing for downstream applications, instead of decomposing the scene with segmentation fields. Then, we would like to get rid of any form of manual annotation effort in the entire pipeline, make it easy for automatic creation of large-scale 3D assets. Finally, we would like to reconstruct object models with accurate surfaces. Among related works, Semantic Nerf and Object Nerf learn semantic fields or instance fields with multi-view segmentation masks for scene decomposition. Follow-up works like Object SDF extends these pipeline for better surface recovery. However, they still rely on relatively accurate multi-view segmentations, which requires manual annotation. Distilled feature fields and neural feature fusion fields distill 2D features into neural scene representations for query-based scene decomposition. However, they still require manually provided queries, and their query-based nature is more suitable for local editing and impedes applications requiring global reasoning upon a scene, such as the decomposition of a salient object. Some works alleviate the annotation cost of multi-view segmentation masks with human interactions and different forms of sparse human annotation like scribbles and seed points. Some concurrent works propose unsupervised nerf decomposition, either in the form of decomposed representations or segmentation fields. However, we cannot obtain object models with accurate surfaces from these methods. Our proposed method fulfills all three desirable properties, make it suitable for automatic creation of large-scale 3D assets and datasets. In the following, we introduce our proposed automated 3D object discovery and reconstruction pipeline in more details. To localize and decompose the salient object in 3D, we firstly reconstruct the semi-dense point cloud of the scene with structure from motion and a semi-dense image matcher. Then, we extract 2D Dino Vision transformer features for each input frame and build point-wise features by aggregating multi-view 2D features. The resulting Dino point cloud is semantically rich as illustrated by the PCA projected colors. Finally, we decompose the foreground object with the SFM point cloud segmentation transformer. Based on the segmentation result, we estimate the ground plane and the oriented bounding box of the foreground object. A dataset is needed for training our proposed SFM segmentation transformer. We propose an unsupervised point cloud segmentation pipeline for automated dataset creation. Given the SFM point cloud with Dino VIT features, we firstly preprocess and downsample the point cloud, and segment it in binary with spectral clustering powered by normalized cut. The segmentations of normalized cut are sometimes noisy. However, since most of the objects are captured on a supporting plane, we can segment the plane from semi-dense SFM point clouds. In this way, we can recover the bounding box of the foreground object for most of the sequences in the CO3D dataset. Based on the imperfect segmentation and accurate bounding box, we can define pseudo-segmentation labels for training. We assign foreground labels to points segmented as foreground and located inside the bounding box. Background samples and similarly defined. Critically, points segmented as background but located inside the bounding box are ignored for supervision during training, as their labels are prone to error. Running the above pipeline on casual object-centric captures can produce a 3D segmentation dataset without manual annotation. Here we show some results of our coarse decomposition pipeline. We show the SFM point clouds with colors and Dino VIT features, and the foreground bounding box estimated with our pipeline. The proposed pipeline can handle various indoor and outdoor scenes with objects in different sizes. After localizing the salient object in 3D and decompose the foreground from its surrounding on SFM point clouds, we reconstruct background-free object model for the salient foreground object. We achieve this by using a decomposed scene modeling and employ explicit regularization with decomposed point clouds obtained in the previous stage while optimizing the neural scene representations. Unlike previous methods that scale the foreground object into a unit sphere with manual annotation of its spatial extent, we explicitly partition the scene into 3 parts with finer granularity without manual annotation, thanks to the estimated object bounding box. More specifically, we use an SDF-based radiance field to represent regions within the object bounding box, and use a NURF for unbounded background regions. Additionally, we use a separate tiny NURF to model regions around the ground plane supporting the object. For scene parameterization, we use a foreground object-aware version of the contraction function proposed in MEP NURF 360 to model unbounded scene. Different from MEP NURF 360, which focuses on the modeling of the entire unbounded scene, we pay more attention to the reconstruction quality of foreground objects. To enhance scene decomposition, we leverage the geometric cues of the decomposed SFM point clouds, including the segmented foreground SFM point cloud and the estimated ground plane, to employ extra regularization for optimizing the scene representations. Intuitively, we explicitly supervise the SDF field to have unsigned distances near to 0, and penalize the SDF field if it represents surfaces near to the ground plane. Combining decomposed scene representations and explicit regularization, we can reconstruct background-free object model with detailed geometry. We evaluate the 3D object discovery result in the form of 3D salient object detection based on the 3D bounding boxes inferred from foreground point cloud segmentations. Ours SFM segmentation transformer performs better than baseline on all 3 datasets, and performs better than our unsupervised segmentation pipeline based on NCut, although trained on a dataset created with the unsupervised pipeline. We evaluate the background-free reconstruction in terms of the extracted mesh and 2D foreground mask renderings. Our pipeline obtains better or similar chamfer distance compared with object models reconstructed by Noose using manually annotated foreground regions. Our pipeline can also naturally render accurate multi-view segmentation masks. It performs better than state-of-the-art 2D salient object segmentation method TokenCut, as well as its multi-view results refined by semantic NURF. Here we show our coarse decomposition results on SFM point clouds and the final background-free object reconstruction. Our pipeline can be applied to both indoor and outdoor scenes. We can reconstruct detailed geometry of foreground objects with complex structures and cluttered background. Our proposed pipeline can also be applied to the reconstruction of human meshes, showing its robustness to different object entities. Thanks for your listening. Please check out our paper and project page for more details.